Okay, so we talked about triple integrals last time. We did a bunch of examples. Remember, whenever you're doing a triple integral, any kind of integral really, there's sort of 3 steps in the process. You've got an application that you're trying to understand. Step 1 is to rewrite the application question as a triple integral. Right? Step 2, turning the triple integral into an iterated integral. That's what we focused on last time, right? So we didn't talk about what applications we were interested in, because presumably that's done. Let's just presume we have a triple integral, turn it into an iterated integral. Then there's also step 3, of course. Step 3 is turning the iterated integral into an answer, a number, right? And that's just a repeated application of the fundamental theorem of calculus. You'll notice we didn't spend any time on that because we've really kind of already done that a bunch. I mean, a fair amount in talking about double integrals, right? But then also massively in Calc 2 courses, right? So let me go ahead and, while we're on that topic, remind you it is assumed that you are strong and comfortable with Calc 2. So make sure that is actually the case. Okay, all right, so now let's talk about some physics applications, kind of the first step in the process. Given a question, how do you rewrite that as a triple integral? We're just going to say a couple of quick words about this because it's mostly the same ideas as with double integrals. A couple of little twists. The location of the center of mass of a solid. Well, now it's a 3-dimensional solid instead of a 2-dimensional region. Right? These formulas are awfully similar to the formulas that we wrote down for double integrals. The only difference is there's 3 of them. Right? So we have a 3-dimensional solid. That centroid has 3 separate coordinates. The other minor difference, of course, is, and this is obvious, is, well, now you're integrating over that solid. So now you have a triple integral instead of a double integral over a 3-dimensional domain instead of a 2-dimensional domain. Okay, other than that, exact same formulas. Okay. Moment of inertia, same formula. You'll notice, and we didn't go through and justify this for double integrals, and I won't do it for triple integrals either. But it's the exact same formula. Make sure to memorize that formula, integral r squared dm. Reminder, what r is depends on the situation. So please don't try to memorize a formula for that r, or a collection of formulas, because there's too many different cases. Right? So what I encourage you to do every time is think about, okay, what is the axis that you're rotating around, and then note that r is whatever the formula would have to be that gives you distance to that axis. So for example, if you're rotating around the y-axis there, okay, well, a generic point there, the distance there to that axis, I can understand that distance by looking at this right triangle. And the punchline there is in that distance, well, of course, what we need is distance squared. Right? So distance squared is x squared plus z squared in that case. And that's just how, that's geometry problems. How do you compute that distance? Yeah?
Why isn't that a triple integral?
Oh, because it's a typo. Thank you for noticing that. Sorry, this should be a triple integral. Make sure to correct your notes if you have a copy of this. Okay. Sorry. Thank you for noticing. Okay. All right. So on the other hand, if you are rotating around the z-axis, well, now the distance, it's different. It's a distance to a different line, right? So, of course, the formula for the distance is going to be different. Now, here we might look at, for example, that triangle, and looking at that triangle allows us to conclude this about r, right? It's different triangle, different formula. Okay. All right. Symmetry. Now, remember, we did a bunch with symmetry theorems with double integrals. I'm a big fan, right? As I explained, I just made so much use of symmetry arguments when I was an undergraduate doing in particular with my physics major. So I want you all to be able to capitalize and have all the same advantages that I did, right? So good news, there is a good symmetry theorem for triple integrals, and it's based on the idea of a reflection, just like double integrals are based on the idea of a reflection. Now, of course, we're in 3 dimensions. The notion of a reflection in 3 dimensions is reflection through a plane. Here's some more good news. This is an even more familiar notion of reflection. Typically, as ideas get higher dimensional, it seems like they get harder to relate to. But this is the notion of reflection that we experience every morning when we look in the mirror, right? So it's an easier concept to kind of wrap your brain around. Certainly more familiar. With that notion of reflection, we can define what does it mean for a function to have odd symmetry through a certain plane. Well, it means that when you take a point and reflect the point, that you get a minus sign in the value of the function. That's the same idea we had with double integrals. The notion of odd symmetry of a function of two variables. Same idea. Okay. Likewise, what does it mean for a three-dimensional region to be symmetric through a plane? Just like with two-dimensional regions having symmetry through a line, it means that if a point in your set, if a point is in your set, then the reflection must be in the set. And vice versa, of course. Okay. All right. So this is a totally analogous set of constructions. The idea of a three-dimensional reflection, three-dimensional odd symmetry, three-dimensional notion of symmetry of a solid. And here's our big theorem. You could even probably guess what this theorem would say. If the function has odd symmetry through a plane, if the domain is symmetric through the plane, the integral is equal to 0. No slicing required, no anti-differentiation required. So massive convenience. Okay. Same warnings that we had before. You have to have both of these apply. It is not good enough to have one. It is so tempting, super tempting to, it goes both ways, to look at a function where you say, look at that function, it has odd symmetry. I'm going to make a symmetry argument. You see daylight, right? You see the conclusion. You get to get an answer to the question, and you didn't have to do, oh my God, so convenient. And it's wrong unless the domain is also symmetric. You're going to make sure to check for that. And vice versa. Just because your domain is symmetric, not good enough. Got to make sure that the function has the appropriate odd symmetry. Likewise, it's got to be the same plane. It's not good enough for the domain to be symmetric through one plane, but the function to have odd symmetry through a different plane. Goes nowhere. Right? The argument does not work. The theorem does not apply. And, such an argument on an exam is not a valid argument. There is no validity to the argument. So be ultra careful about that as well. Okay, the Riemann sum point of view, I'll be quick about this because, it's morally the same point. The symmetry of the domain ensures that for any given region, there is a corresponding little region on the other side reflected through the plane in question. And thus, for every term there is a corresponding term at the reflected point. Right? The odd symmetry of the function guarantees that these are negatives of each other. And if they're negatives, then in the summation, they cancel. And all the terms cancel, and the Riemann sum adds up to 0. So same argument, morally equivalent argument anyway. Okay. All right. I'll show you an example of how to do this. Suppose I wanted to compute a triple integral like this. Note that my domain here, my domain is the unit ball. Let's take a quick pause before we go on to speculate on how hard this might be. Let's go back to when we did the appropriate slicing for the unit ball. Here it was, right? Suppose your region's a unit ball. Here's what our integral ended up being. Look at all of these square roots. All those square roots are going to get into the integrand then of the next most outside integral. Right? So this could be brutal. Really brutal. Okay. Where am I? Here we go. Okay. So rather than deal with that nightmare, we're going to make a reflection argument. Let's use the XZ plane. I'll come back in a moment and talk about why I'm using the XZ plane. But let's just say There's the XZ plane. What is the formula for reflection through the XZ plane? Now, this is a geometric appeal. I mean, very often, usually, in fact, I'll say, the kinds of symmetry arguments that we're going to make are such that the corresponding reflection is kind of just a matter of looking at the picture and thinking it through. Right here, if you have this point, x, y, z, the reflection is just it's going to keep the same x coordinate, it's going to keep the same z coordinate, and the y coordinate is going to turn to the negative of what it otherwise was. Right? Easy conclusion from the picture. Is everybody happy with that? Okay. Alrighty, what happens when I take this formula for reflection and plug it into the function? Well, my function is this thing. What happens if, everywhere I see a y, I put a negative y, right? So that's what our reflection is doing. Let me pencil this in. Everywhere I see a y, I'm supposed to put a negative y. I get a minus sign in there. I get a minus sign in there. That factor y squared sort of kills the minus sign. That goes into that y squared factor. But sine y is another odd function. So sine of negative y is negative sine of y. And so in this calculation here, where we're evaluating f at the reflection point, that is negative sine y. Yep. Yeah. I'm going to get to that in a couple minutes. Yep. Totally. Come back to that. So what we have, the function, though, you do this calculation, take the formula for the reflection, right? Plug that in. Compute f of r. Notice you get negative f of x. And therefore f has odd symmetry. Last observation that we do have to make, again, there's temptation to spike the football. Right? We found a plane, we did the reflection, the function's got odd symmetry, you want to declare victory, move on to the next question. Be careful. Got to make sure that your domain has the appropriate symmetry as well. And by the way, you have to also say so, right? It's not enough for it to be true. Remember, exams in this class are not a matter of do you get the right answer at the bottom, right? Exams are a question of is your argument valid and complete and clear, right? So you do have to say the domain's symmetric too. Right. So that being the case, though, we've checked all the conditions of the theorem. Triple integral 0 by symmetry. Now spike the football and move on. And we didn't have to deal with any of the square roots that we were afraid of due to the ugliness of the domain. Yeah.
So you don't have to prove that the domain is symmetric.
Yeah, right. So, right. So let me talk about what you're responsible for saying on the upcoming midterm exam, at least, and I might revise this for future exams. But for the upcoming midterm, at a minimum, here's what I want you to make sure to indicate: what plane. You're going to be very specific. What plane are you citing symmetry through? The same rules that I had for double integrals, by the way. What is the plane? What is the formula for the reflection? I want to see a complete confirmation that the integrand has odd symmetry. And I want to see at least an assertion, scratch that, a correct assertion that the domain is symmetric through that plane. Yeah, you don't have to justify the symmetry of the domain. That's usually just a matter of, really it's just a matter of looking at the picture, so it really is by inspection. And so no justification required there. You have to be correct. All right, everybody on board with what's required? So this is what I'll consider a fully complete argument, symmetry argument for that you might want to use for this next exam. Yeah.
Are there examples where the plane that we're going to reflect it on is not necessarily the XT?
Oh yeah, sure. I mean, so we did one back with double integrals where the reflection was over. One that was 45 degrees, you remember? And so the formula for the reflection there is that the x and the y kind of trade places. So stuff like that. But if you want to talk about, how, is there a scenario where you might have to reflect through some wacky plane like that? That's a harder problem, and exactly how to go about doing that is beyond what we could reasonably expect in Math 212. So I would call that not a reasonable question. Unless, maybe I could imagine some scenario where I, give you that formula for that reflection or something like that. Or give you enough tools that it would, where I give you most of what you need to make that, something like that. But most of the time it's should be a situation where the reflection's easy to determine. Okay. All right. So the question came earlier. How did I know to use the XZ plane? Why didn't I use the YZ plane? Why didn't I use the XY plane? And so let me give you my motivation. So we're going to sort of step away from math and talk about strategy. Right? So strategy. We're looking at the unit ball. I know that the plane that I pick has got to be a plane over which this unit ball is symmetric. Good news! The unit ball is crazy symmetric. It's symmetric. In fact, it's symmetric through any plane through the origin, right? So let's not worry about that first. That's the easy problem, right? To make sure that the ball is symmetric. Let's worry about our integrand, right? And let's ask, algebraically, what kinds of things could I do to the variables in this formula? Just, thinking out loud. That would make this turn negative. What would happen if I replaced all the x's with negative x's, for example? And the answer is nothing, right? You turn x into negative x in that formula, that negative gets squared, and the function does not become the negative of itself. So whatever plane, don't even worry about what it is, but whatever plane would have been the plane whose reflection would make x turn to negative x is not what we want. So we don't have to go down that road. Likewise with z, if you turn z into negative z, nothing happens, right? In fact, there are no z's in that formula. So that's not something we need to deal with either. And then you make the observation that, hey, check it out. If you stick a minus sign on that y and on that y, then in some sense I get an extra 3 factors of negative 1, and 3 factors of negative 1 is a negative. Right? So strategically, the first thing I do is, looking at that formula, I realize that this is what I really want. Right? So in my, strategic thinking, I came up with the formula for the reflection first. And then I sort of worked backwards and said, okay, all right, well, this is my wish list. I hope, fingers crossed, that there is some plane out there, reflection through which is given by this formula. How am I going to figure out what that plane is? Let's draw a picture of this reflection. This reflection says that point reflects to that point, and now we've got sort of a little, geometric intuition challenge. What plane is it that reflects like so? And then not hard to persuade yourself that it's the XZ plane. Okay?
So is it possible then that even though both of these tests fail, it's still possible for the triple integral to equal 0?
Yeah, of course. Yeah. So when the symmetry theorem applies, the integral is definitely 0. But it is certainly not the case. And no one's suggesting that just because the integral is 0, that it has to be due to symmetry. Right? There's plenty of cases of integrals that are 0 just despite complete lack of symmetry. Yeah, totally. Right, absolutely. Okay. Okie dokie. So persuade yourselves that you can't use the YZ plane or the XY plane. I think it's a nice little exercise. We've kind of talked through part of that already. Nevertheless, a good thing to sort of write down what specifically fails. Okay, so done with triple integrals. We're going to move on now to change of variables. This is a big topic. We're not going to finish it today, not even close. There's a lot to say. I like to segue into change of variables by talking about single variable calculus a little bit. Of course, I do that a lot, right? We motivated double integrals by talking about single variable integrals. We motivated derivatives, directional derivatives, all that kind of stuff by kind of initially talking about single variable derivatives and trying to extend those ideas. So it turns out there is a kind of a single variable version of change of variables, this new thing called change of variables. So we're going to be extending an old idea here. The old idea is called the substitution rule that you all remember from Calc 1. Okay. All right, so in order to be able to make that argument, though, I'm going to have to lay a little bit of groundwork. Y'all remember the whole deal when you're integrating, you take an interval and you chop it up into little pieces, right? And we did it like this, where all these pieces that we chopped into were the same size. Now, why did we make them all the same size? Well, because it's convenient, and turns out that it doesn't matter anyway, at least for a very, very, very large category of functions. Most functions that you're going to deal with, doesn't matter. So we go with the convenient option. That said, I do want to recognize that, in fact, it really, in fact, does not matter. It is also true that if you were to take this interval and chop it up in an irregular way, if you were to, make some of these pieces clearly bigger, some pieces clearly smaller, right, et cetera, et cetera. And as long as you keep slicing, as long as it, in the limit as you go, as long as it's true that the size of the largest piece approaches 0. I mean, obviously, don't sit here and keep slicing, just like this, finer and finer within it, but leaving this great big gap. Obviously, that's going to leave massive round-off error, right? So as long as you keep slicing in such a way that the biggest piece keeps getting smaller in the limit, right? So no pieces get to just stay there and be huge. Right, something kind of along those lines. You're going to get the same value as if you did the regular slicing. And you might think to yourself, my gosh, who would do that? What kind of sicko, right, would go to the trouble of making highly irregular slices? And I agree. My gosh, why would you do that? It's hard to see this coming, but it turns out that even though this is less convenient for calculations, it turns out that sometimes it's more convenient for making interpretations of intervals. Right, so I have to get this groundwork laid because that's going to happen to us here. We're going to find that we are going to be doing an interpretation of single variable integrals where kind of unavoidably the pieces are not all the same size, and it's not our fault. And it's going to be very convenient to say, and furthermore, that doesn't matter, so we proceed. So, all right. So, substitution rule. I claim that this is sort of, the what we're going to be generalizing going forward. So let's remind ourselves what that is. Y'all remember the substitution rule? I'm sure you do. It's like the first integration technique that people see in Calc 1 classes. And the idea is that, okay, if you want to replace some variable u with some function g of x, or vice versa, if you have some function in your integrand called g of x and you want to just rewrite that as u, then go ahead, right? Note, we still, morally in some sense, we haven't done anything. We're still writing down f of g of x. Just rewriting the g of x is something else that we've already freely admitted to, right? The only little asterisk is don't forget to rewrite your differential accordingly, right? And if u is equal to g of x, don't forget that du dx is g prime, and thus du is g prime of x dx. Okay, so this is how it gets presented very often in Calc 1 classes. I have my quibbles with the issues of how this is presented. There's a certain sloppiness about this, and I would love to talk about. We just don't have time. It's not really a Math 212 thing, but nevertheless, this is a common point of view. You can also use the chain rule to justify this in a way that's a little better, really. Okay, nevertheless, very familiar. How do we justify this? Sorry, I got ahead of myself. Excuse me. Also, don't forget to plug in your bounds. So, for example, this a right here. What do I do with that? What do I put over there? Don't forget that when you put an a there, you're talking about a value for x. So plug that in to convert it into a value for u, knowing that A is a value of x, you see that the corresponding value of u is g of a. Right, and that's just a plug-in deal. At least that's a point of view on it. Right? Okay, with that said, I want to give you a different point of view about these bounds and about where did this come from. That goes directly to the Riemann sums. Again, this is not me being rigorous. This is me wanting to lay some groundwork for an idea that will extend to Math 212. Right. So this is an important sort of look back. So a different point of view on these things. So let's think of G not just as an algebraic sort of tool. Right, but let's think of G as a function that's literally taking points on the x-axis over to points on the u-axis. Like so. Here's G. Right, and it takes x values and returns u values. Okay. And let's start talking about how would I do an integral? Well, if I take this interval here on the x-axis, what happens to the starting point? Well, that starting point goes over there, and this ending point goes over to there, and A clearly goes to G of A, B clearly goes to G of B. Okay. All right. What happens if I chop? Right. So let's imagine taking this interval from A to B and chopping it up. Right, as we usually do. Well, notice that each one of these points has a corresponding image over here. Right, so when you partition, in anticipation of doing an integral, when you partition the interval on the left, you're indirectly sort of effectively partitioning the interval on the right. And here's where this irregular partitions business comes up. This is not a linear function. Right? So even if I go to the trouble of making sure that this is a regular partition, this over here probably not. Yeah, it's just G some wacky function. So who knows? This could be a highly irregular partition. Good news, we don't care. Right? Okay. Alrighty. Okay, so I want to talk about how big are the pieces over here in this this partition. So let's, whichever one, some arbitrary piece over there. That piece came from this piece, and what's the relationship between the size of that green piece and the size of the yellow piece that it came from? Said differently, what did the blue function, G, right? What did G do to that yellow interval to turn it into the green interval? How much did it stretch it out? Or, squish it down, however you want to say it. Okay. So here's the picture that I'll draw for that, just to sort of, there's our original little piece. Here's the stretched out version of that piece. And we've given a name to this. We've called that delta x. This thing over here I'm going to call delta u. What's the relationship between them? I'm going to flash you back now to chapter 13. Don't forget that derivatives turn input changes into output changes. Right? And even though we think of this as a size, we think of that as a size, notice you could also think of it as a change. Namely, how much did x change in going from here to there? I can think of delta x as a change in x. And the derivative then tells me what is the corresponding change in g of x, namely, what's the corresponding change in u that we've called delta u. So multiplication by the derivative does that for us, and so back to this version. So delta x, what you do to delta x to infer delta u is you multiply by the derivative of that function. You multiply by g prime. There's our g. So the derivative of that g function gives us what I'm going to call the stretching factor. How much did that little yellow interval get sort of stretched out as a consequence of what that blue function did to it? Yeah? Everybody cool? Okay. All right, so multiply by the derivative is the stretching factor. Okay, well, so what I'm going to do now is suppose that I've got some integral on the u-axis. There's my u-axis. Suppose I'm doing an integral there. By the way, don't forget, this is how we write integrals. Well, we have a shorthand. Right? But this is what an integral is. An integral is a Riemann sum. So on that u-axis, between the starting point and the ending point, we are slicing it up. And on each piece, we're writing down this expression, whatever f is, who cares, it's application dependent. F evaluated at one of those corresponding points times size delta u, and take a limit. Okay. And the observation I'm going to make is that I can take that expression and rewrite all of it in terms of x. Everything here is written in terms of u, but I can rewrite all of it in terms of x because that's what the substitution is. The substitution tells me that u is g of x. So I plug that in. That's perfectly legal algebra. It's just literally just algebra. Right? And then from what we learned on the previous page, right, over here on the what colors did I forgot the colors. Let me use yellow for this. This size I can rewrite in terms of x's like so, and or said differently by inserting the stretching factor. So delta u is that. All right, so plugging in the blue plug-in, the yellow plug-in, it turns that Riemann sum. Here we started with an integral on the u-axis, namely a Riemann sum, and notice that it has turned into, I hit the wrong color. It's turned into a summation over the corresponding points on the x-axis. Namely, it has turned into an integral. So this is Riemann sum notation. I like to start with Riemann sum notation. So just as a reminder, we're literally chopping things up into little pieces and trying to figure out how to rewrite the calculations that are going on the little pieces in the u-axis and rewrite them as calculations that happen over on the x-axis before we then transition to saying, yeah, okay, fine, then what that means is that this u integral turns into this x integral. Okay. All right. Alrighty. And then, by the way, now you can see explicitly why it is that these bounds a to b turn into these other bounds g of a to g of b, because that's what the function does to the interval. Okay. All right. Now, why did I just give you a bunch of time spent on Calc 1, arguably Calc 1? And it's because we're going to do this exact same thing now in a multivariable context. And I say exact same thing. Well, it's not exact, of course. It's going to be a little bit different. Context is going to be different, so that's going to be, double integral instead of a single variable integral. But the big ideas are going to be the same. Now, let me point specifically to the big ideas that I claim that we're talking about here. One is the idea of how these pieces stretch out. So this piece here stretches out to turn into a little piece here. There's a factor that allows me to keep track of, how much did that stretch, and the derivative is the factor by which size stretched. So we're going to do something along those same lines in a two-dimensional setting. So we're going to carry this forward, the idea that little pieces on the left turn into little pieces on the right, and they can be viewed as having their sizes stretched by a factor. Okay. The next idea is, and of course all the details are going to be different, the next idea is that, with a stretching factor identified, there's our stretching factor in this case, with a stretching factor identified, whenever you have a, u as a function of x, whenever you have output variables as functions of input variables, you can just do this and this right, and effectively turn an integral on one domain into an integral on a different domain. And this is what we call doing a pullback. This is the term I like to use. It's a common term in other contexts that are not unlike this. So pullback. The reason this is called a pullback is because it seems to go backwards. I mean, let's not lose sight of the function let's not lose sight of the fact that the function goes that way. The function takes values on the left and turns that into values on the right, and yet, weirdly, the expression goes the other way. So expressions in terms of output variables, by plugging in, effectively turn into expressions involving input variables. And that's a little counterintuitive, right? It feels like, look, the function goes to the right. You give me stuff on the left, I turn it to the right. Point on the left, point on the right. Wouldn't it seem like expression on the left, expression on the right? And it just isn't. Right? Plugging in, the act of taking u equals g of x and sticking that in and plugging in, actually turns expressions of u the other way back into expressions in terms of x. So it seemed, I mean, this is what happened. Right? So, like I say, it's a little bit counterintuitive, but this idea of a pullback is a big deal. This is going to show up dramatically in how we make use of this idea in two-dimensional and also three-dimensional contexts. So those are the two big ideas to keep track of. The idea of a stretching factor and the idea of a pullback. Okay. All right, and here we go. Two-dimensional setting. Let's consider this scenario where we have a domain, let's say in the UV plane, and then we have some function with two input variables, two output variables, some function of u and v whose outputs are x and y, let's say. And let's imagine what happens to this domain D if I take this domain, all the points of that domain D, cram them into that function called g. Well, out's going to come a bunch of points, and it's probably not going to be a rectangle. It's going to be some bent, twisted, contorted, I mean, you sort of expect, corners might still look like corners or something like that, right? But it's going to be all twisted and distorted, generically. Okay. And so what we're going to ask is, can we apply the two big ideas from the last page to this new context, right? This is no longer turning an interval into another interval. Right? Now we're turning a domain into another domain. And so here's the question we ask. Step one, can I look at a little piece over here, talk about the size of that little piece, talk about the size of its image, and is there some factor, is there a stretching factor that I can write down that'll tell me what do you have to multiply by that purple area to get the yellow area? Same idea. That's what stretching factor was over here. The stretching factor is that what you have to multiply by the purple length in that case to get the, I used green here, to get the output length. Input size to output size. So analogous here, is there a number that multiplies by input size to get its output size? So that's a problem that we're going to have to consider. Next question is, does it follow that I can take an integral defined on this domain, and can I pull it back? Can I take an integral defined on that ugly green domain? Ugly! Look at all the curves and twists and corners, and oh my gosh, think about slicing that up, and how many different integrals are we going to have to turn that into? Yikes. Right? Can I turn that instead, fingers crossed, into an integral over this original domain, which, look at least in the case I have drawn here, a nice pretty little rectangle. Everyone's favorite domain for a double integral. The bounds are constants. Super convenient. Okay. And the answer to both these questions is yes. And here's some details. The big question is, what is the formula for the stretching factor? The thing that stretches out input size to output size, that which you multiply by, oh gosh, I'm losing track of which colors I used. I think I used purple here. That which I multiply by that area to give me this area. And there's a formula for it. And I'm not going to justify it right now. I'm just going to assert it. We'll talk a little bit later about how to justify it to some extent. But right now I'm just going to assert what that formula is. And the next question, does that subsequently turn one of these integrals into a different integral? And yeah, totally. Check it out. xy, I used green here. xy is g of uv. Right, that's what that says. U and v are the input variables, x and y are the output variables. So, yeah. And this area over here, as we just discussed, can be, details to come, viewed as a stretched out version of the area on the left. So the pullback strategy is going to work just fine. Yeah.
So just to be clear, in the example before this, you used U as the...
Oh, yeah, I made some choices on this a long time ago. Part of my decision was based in, what's typical in Calc 1 classes, and the other part of my decision was based on what is our textbook using. And it seems that there is a sort of a reversal. But those are just letter choices. It doesn't matter. So it's part of your job as a math student is to don't get attached to certain letters playing certain roles. That's a mistake, right? So always take an active eye to, wait a second, which variable name is playing which role in this scenario. And this is going to happen a lot through, application, courses that y'all will all take here and there, that it's not always y as a function of x, and it's not always, u is g of x, and sometimes the input variable is t, sometimes the input variable is y. Right, etc. And sometimes the substitution's not U. Sometimes the substitution is K, and such. Yeah. Right. Yep.
So in this case, you're given the domain on the right. Right?
Yeah. So so in this case, what we're doing is we're viewing. I'm going to say we're starting with, in some sense, that domain, and then we're, by the application of this function, turning it into a new domain, and we've found here a relationship between the integrals on those two different domains. Now, which one you're going to be given in a question, like in an exam question, different story, right? Right now, I just want to observe that we're sort of, if we view it as we're starting with the yellow, there is a correspondingly produced purple, then we can find a relationship between integrals on those domains. Yeah. Okay. All right. So the big looming question, what is the formula for this stretching factor? And here's the formula for that stretching factor. Justify this later. For now, you can just take this as a given. It's the absolute value of the determinant of the Jacobian matrix of the change of variables function g. That's how it turns out. By the way, ultimately, very natural. There's great reasons for this that we will see later. But for the moment, I want to take that as a given. Don't forget, by the way, that the Jacobian matrix, we talked about this back in chapter 13. Jacobian matrix at that time was a very convenient tool for helping us keep track of the chain rule. It was a matrix which allowed us to sort of reinterpret the chain rule as giving us a relationship between input velocities and output velocities, right? So the Jacobian matrix was a matrix that played a role with derivatives back in chapter 13. No surprise, I suppose, that it ends up playing a prominent role here. Just don't forget, the stretching factor is not the Jacobian matrix. The stretching factor is the determinant of the Jacobian matrix. Correction, it's the absolute value of the determinant of that Jacobian matrix. Okay. Beware. This is a little awkward. The book makes a different notational choice. I'm uncomfortable with the book's choice here. The book refers to the determinant as the Jacobian. To me, it's just a terminology, a notation thing, whatever, right? To me, the Jacobian is the matrix. To the book, the Jacobian is the determinant of the matrix. So heads up, watch out for in the book you're gonna be like, hey, how come they didn't take the determinant? To them, the determinant is part of what they call the Jacobian. So this is super annoying, but yeah. Yep.
So does the ordering matter? Like the ordering of, like if I...
Of what, the elements inside the Jacobian matrix? Oh yeah. It's got to be just like it was in chapter 13.
I'm talking about like if we put the partial of y as like the first row and the partial of x as like the second row.
Yeah, everything matters. I mean, those four elements have to be exactly where they are. Right? Absolutely. Yep. To be a Jacobian matrix. Yeah. Right. Okay. Now here's another notation that I think is nice, and I like this a lot, and I encourage you to consider using it. And that is to observe that this. I'll use a different color. This Jacobian determinant, I'm not including the absolute values in what I'm talking about here. To rewrite that Jacobian determinant as that sort of fraction-looking thing. Let me show you why that's handy. All right. What we're talking about here is something that you multiply. I'll just do it up here. Something that you multiply times du dv. I don't like that color. Something you multiply times du dv to get dx dy. Now let's notice what happens if what that is. If I write that as partial xy, partial uv, and of course let's not forget our absolute values. What happens then, in a seemingly appealing bit of notational good fortune, it's almost like the UV cancels with the other UV, and what's left is just the XY, which of course is, oh my gosh, not really what's happening, right? This is not really a fraction. Look at it. This thing here, that is not a fraction. That is a determinant. Determinants are not fractions. So, oh my gosh, no, it's definitely not a cancellation, right? So this is let's be perfectly clear about that. That said, it is awfully convenient to way to, memory tool, if nothing else, to just pretend it's as if there's a cancellation. Victimless crime here, and then we see the seemingly the XY show up. So anyway, it's nice for a combination. We'll see examples where that is particularly convenient. Yeah. But heads up, this is another very common choice. Yeah. Okay, let's do an example. We have a minute. We won't finish this example, but change of variables is actually a somewhat plug and chug process. At least in some cases. So here, we're going to start with a unit square. And to that unit square, we're going to apply this change of variables function, g. There's the formula for it. And note that the result is this domain R, whatever that thing looks like, a letter opener or something. Certain kind of drill bit, if there's any carpentry people in the room. So what can we say about, what does the change of variables say about this situation? Or let me put that a little bit differently. Let's suppose that I find myself faced with an integral defined over here. I'm interested in some integral in that domain. How would I compute an integral on that domain? And let's observe. What a nightmare. Think about the slicing process as you're slicing through there. Okay, you're going to hit that corner. And then you continue slicing up, you're going to hit that corner, and then you keep slicing. So you would have to have three separate integrals if that's what you wanted to do. Furthermore, notice that the pieces there, this curve, it's not clear what the equation of that curve is. Right? I'm viewing it, I've kind of got a parameterization sort of that curve, but I don't have an equation for that curve. And so as I go through and do my slicing, I'm going to need to solve for, y is a function of x, or x is a function of y, depending which way you slice. And I don't have an equation. This looks like a bummer of a question to have to deal with, to slice this up the old-fashioned way. So what we're going to do instead is use a pullback argument. And so the pullback argument says that the integral on that yellow domain, I can pull back and say, forget about the yellow domain. There's a different integral that you can do on the green domain, your pullback domain, and that different integral will have the exact same value. So we don't have to do an integral on the yellow domain. We can instead do an integral on the green domain. Now, what do you think? What your personal preferences? Which would you rather? No contest, right? Everyone would rather do it on the nice, pretty green rectangle, right? So it's going to be a big win, and it's just a matter of plugging in. Now we do have to take this g function. We've got to compute the stretching factor. That's just some partial derivatives. There they are. Take the determinant, take the absolute value, and this turns out. Oh, I'm out of time, aren't I? Anyway, it turns out to be this, but there's some more things I want to say about this. So we'll pick up here on Friday. Y'all have a good Wednesday. See you later. I owe y'all an email about homework. I will make sure to send that email before today's over. If I don't send that email by 5 o'clock, please feel free to remind me, and I'll appreciate it.